So, okay, so what did we do last time? We talked about, this is all working. Hooray. I found a much better iPad mirroring app now. Seems to not crash. It's great. So last time we talked about root binding. And then we did Newton's method. And then we talked about minimizing what we're going to do in here because we're controls people. We minimize things. You want to do RL, you can maximize things. That's cool too. And then we talked about, remember we did this example where the Newton solver went uphill instead of downhill. We talked about all that. And so then we talked about this idea called regularization, which basically forces Newton's method to go downhill always, right? Okay, cool. And then at the very end, we showed this example where we did the regularization thing, so that made it go downhill, but it overshot the minimum, right? And so that was kind of the teaser to carry us over to today. So today we're going to go fix that problem, the overshoot problem. And the way you do that is with something called a line search. That's the first thing we're going to do today. And then we're going to start talking about constrained minimization, which is super important for us. We're going to talk about equality constraints first, and in our context, that's how you do dynamics actually. So we minimize a cost function subject to the dynamics. So those are equality constraints. Then we're going to talk about inequality constraints, and where those show up for us are like two major things. One are actuator limits, like torque limits. You need to stay within your actuator limits, and the other big one are like things like obstacles, safety constraints. Like so you have control constraints, right? U has to be like say less than equal to some U max kind of thing for your actuators, and then you have like don't hit the walls or slam into the other car type of thing. State constraints, those are inequalities, right? Okay, so any question about any of that stuff? And then if we have a little extra time at the end, you asked some questions about like gradient descent and fixed point iteration, so I have some extra fun stuff for that if anyone wants to. If we got some time, I'll do it at the end. I'll show you guys after. There's some cool things in there that yeah, the gradient descent story is clear, but the Newton story there is actually really fun, and I don't think it's in the literature. Like I worked this out, I was like, oh, I haven't seen this before. I wonder if there's a paper, and I didn't see anything. So that might be a fun paper if anyone wants to do that for the class project. Turns out Newton's method is deadbeat control. Has anyone heard of deadbeat control? Yeah. So Newton's method is doing deadbeat control on a linear approximation of the dynamics. That's what it's doing, which is cool. And I Googled this and there was nothing. So if anyone wants to write that up and have a paper, it's fun. It's where you try to zero out your error at every time step. So it's like if I'm here, like if I'm trying to like regulate my system to the origin, I have some state error. You just try to like zero out your error every time step. You're just like, okay, here's where I am. So if you're fully actuated and you're a linear system, you can do that instantly at every time step, right? So in a discrete time system, you're just like, okay, here's where I am. That's the goal. I'm just going to go right to the goal at every, right now in one step, or in the minimum number of steps possible, right? So we can talk about that at the end if there's extra time. I just got excited about that because I thought it was cool. And it came from your question. So thanks for that. Someone should write that out. Too fun. Okay, cool. So let's talk about the line search thing. Okay, so yeah, basically like we saw at the end last time, often on like nonlinear stuff, your delta x step from Newton's method will overshoot the minimum. And you can actually, if you're like particularly perverse, you can engineer situations where it'll just zigzag forever and never land at the minimum, which, is evil, but you could do that if you wanted to, right? Cool. So basically what we're going to do to fix this is like a very straightforward thing. It's like most of these things are fairly intuitive, right? The regularization thing is like, okay, Hessian's indefinite. We're just going to pad it until it's positive definite and all good. This is a very similar hack that's, simple, but basically what you're going to do is you're going to get your Newton step and you're going to plug it into your F and try it and see what happens. And then what you're going to do is backtrack, i.e. decrease the step length. So you're going to go in the same direction. You're just going to put an alpha step length in front of your delta x and shrink the step size and backtrack in that direction until you get a good decrease of F, a decrease that you're happy with. And so there's like a how do you define good decrease, kind of question here. We check F at the new step and backtrack until we get a quote good reduction in the cost in F. So you can imagine this is like a pretty simple idea, and there's many ways you could imagine implementing this, right? So there's the question of how do you define good here, right? Is the main question. And in particular, what you want out of your good step length is something that's going to guarantee convergence. That's going to guarantee a good decrease and ultimately like asymptotically guarantee that the thing lands on the minimum, which in the zigzag situation, you can, again, have corner cases where it will never land on the minimum. It just keeps overshooting and zigzagging forever, right? Okay, so kind of the simplest strategy that actually works and gets you that convergence guarantee, because you imagine like a simple idea would be to just say, backtrack until I get anything that decreases the. It turns out that's not good enough. And you need a little extra. And so this is like the simplest thing you can do, the simplest little extra that actually guarantees convergence. And this thing is called the Armijo rule. Anyone heard of this before? Nobody. Okay, cool. So here's what you do. We start with a step length of 1, so alpha equals 1, which is our, like basically just saying take the full Newton step. So this is step length. So we try a full Newton step. And then here's the conditions. So we do. So right, naively, we might say, well, this is, worse than where we started. So for sure, you want to be less than the last f of x, right? You want to do better than before, at least. Turns out you need a little more than that. And so the little more is the following thing. So I'll write this out and then I'll talk about what it means. Okay, so it's you want to do a little better than last time. And the way we define a little better is with this thing, which is checking the linear, it's some like basically tolerance on how much decrease you should have gotten if the linear approximation of f were true. So grad f there is the linearization of f, right? So I check grad f times delta x. So that's like how much f should have decreased if it were a linear function, if my first order Taylor expansion were true. Alpha is my step length, right? So alpha times grad f times delta x is exactly the decrease I should get under the linear approximation. And then B is basically a tolerance, like a fudge factor. So what this is saying is I want to get a decrease of f with my step that basically agrees with the linearization within some tolerance B. That makes sense to everybody? So basically, yeah, I want to get it to decrease. I want it less than where I started, but I need it to decrease sort of a sufficient amount. And sufficient amount here is like basically within some tolerance of what the linearization said it should decrease by. Okay, so this B thing is that tolerance. And then this whole term here is the like expected reduction from the gradient, from the linearization. So we try this, and then we just backtrack. So we just chop down the alpha by some factor, say a half is like a good default choice until that condition is satisfied. And this C is like, some scalar that's less than 1. And so, yeah, usually like a half choice. Okay, so that's, and so intuitively, what we're doing here is we're making sure the step that we're taking agrees with linearization within some tolerance. B. And then like typical values for all those constants, let's say are like C is a half, right? So you basically chop the step size in half, every try. And then that tolerance B is usually pretty bad, actually. Like we're really usually pretty happy with pretty coarse tolerance. So it's like 10 to the minus 4, but somewhere between 10 to the minus 4 and like 0.1. It's like a pretty typical value there. So we're pretty loose about the tolerance. Like you don't need to be super close, but you've got to get like at least a little more decrease in there than just the last value is kind of the idea. Okay, so any questions about that idea? And there's lots of other fancier ways to do this. This is the simplest way that actually works. There's fancier ones if you look into them. Essentially, the fancier ones are just taking more terms in the Taylor expansion, though. So this one's like basically the gradient descent version. The next kind of fancier set are called the Wolf conditions, and those use the Hessian as well. They're kind of checking the second order Taylor expansion that you're actually using in the Newton step. They're basically checking if that agrees with the actual decrease within tolerances and stuff like that. Okay, so we're not going to do that, but you can check it out if you're into it. So here's the code. So we're going basically it's the same stuff as last time. Same function we're trying to minimize. The plot, right, as last time. So we're gonna go do the same thing as last time where we start there. This is the bad one before we regularize. So here's the regularization version. So we start there, we overshoot, right? And then like eventually, so that's the overshoot that we had last time. And then it sort of settles down, right? And we don't want to overshoot. So this, took that giant overshoot step and then kind of settles down within 4 or 5 iterations. Cool. So I was at the end of class last time. So here's the full up thing. This has all the tricks now. So this is our Newton step with regularization and backtracking line search. And this is basically it. This is like all you need to make this work on general nonlinear things. So we're using that tolerance in the line search. We're setting that to 0.1. Our backtracking parameter is a half. This is our regularization parameter, which is 4. Then here's the whole thing, right? So we check our Hessian, make sure it's positive definite. We pad it till it is. That's what we did last time. So that makes sure we get a decrease. Then we compute our Newton step right here. And then here's our backtracking step. And this is exactly what I wrote down, right? So we're going to take the step and evaluate our cost, F. And then we're going to check that it agrees with, it's basically we need more decrease than what the first order Taylor expansion says with that tolerance on it. Everyone cool with that? And then we try this, we backtrack by a half till it works. And then once it works, we take the step. Let's go ahead and try that. So we'll start over again from like that original starting point. And remember, we overshot a bunch last time. Let's see what happens now. Oh, oops. We can start this over again. Okay, so there you go. So basically, instead of jumping all the way across here, this gave us now just a straight up decrease and got like really, really nice step almost to the minimum. And now, there's 2 steps, 3 steps, and we're good. We nailed it. Right? So that's exactly what you want to see. Right? This is like the whole thing. Yeah. So yes, and without this, you're actually not actually guaranteed to converge to a local optimum. That's kind of the big thing, right? So we showed in this case, it overshot a ton, right? And then we happened to get lucky in this case because that overshoot point was still in the basin of attraction. So it still worked. But there's cases where that overshoot can just like send you off to who knows where, and you just bounce around forever and never land it. And so it's pretty easy actually to cook up situations where so you have a minimum and you have 2 kind of flat spots on either side. You can like zigzag like this. You can create perverse examples of F's and like starting points where Newton will just do this forever. Or like in practice, you can get situations where it zigzags and ends up making like horrible, really slow progress because of weird functions. That's right. Basically, the whole point of that extra term is to prevent it from zigzagging. This guarantees monotonic descent. Yeah. So the Hessian padding regularization thing that guarantees a descent direction, but you can overshoot and bad things can still happen. This guarantees a monotonic descent. So this makes sure you're always making progress towards the minimum. Yeah. So these are actually super cheap. Yeah, like this line search thing, like I'm evaluating F a couple times. Like the gradient I already have, right? Because I used that already. So line search is super cheap. It's just like a handful of F evals. Yeah, so it's worth having this chat, right? So in Newton, the most expensive thing by far is evaluating and factorizing the Hessian. So the Newton step, we had to calculate the Hessian. So if you're doing a big problem, computing the Hessian and then factorizing the Hessian, like solving that matrix inverse thing, is way more expensive than any of this other stuff. That's the expensive part. The line search is dirt cheap compared to that. The regularization stuff, if you're naive about it and you're refactorizing every time you update the regularizer, like then you're basically having to solve that expensive part over and over. You don't want to do that, right? And that avoiding refactorizing is the game here. And there are clever tricks for doing the regularization stuff without having to refactorize, where you can kind of do it inside the factorization and cheat a little bit. That's what you want to avoid. All this other stuff is like window dressing stuff. It's in the noise. So as long as you're not doing multiple factorizations, all this other stuff is cheap. You always do these things. Like, so on a non-convex, like nonlinear thing, this won't work without those two extra tricks. You need regularization and backtracking always. You always have to do it. Otherwise, it won't work. That's why we're talking about it. This is not just for for kicks. It's actually important stuff. The other stuff about weird deadbeat control, that's all whatever. That's all for fun. This is like actually important. Okay. You want me to try any other weird stuff here? Or, go play with the code for sure with all this stuff. But so yeah. Over here somewhere. Oh, this one was in that basin of attraction, remember? So this one would have gone up without the regularization. So the regularization forces it to go down, but then it overshot over here. So what we did then is we add the line search, so it ends up down here with the line search, right? So yeah, you need both things always. Always do both things. All right, everyone cool with that? Basically, every time it fails. So I try it at alpha equals 1. So I try the full Newton step. If that fails the Armijo condition, if I don't get the sufficient decrease, then I chop it in half. Then I check again. And if you always, all you're doing there is just shrinking the step size by half every time. So you try it. If it works, great, you're good. If it doesn't, you shrink the step size by half, try again, evaluate F again, right? Check the condition again. If it works, great. If not, check again. Yeah. That makes sense? Yeah. Yes. Yeah. So what this is doing is like guaranteeing descent, right? The idea here is like both of these tricks are really only necessary when you're far from the optimum. When you get close at the end, you really shouldn't be doing this. Like these things should basically, these are called what are called globalization strategies. They're important when you're far away from the optimum and you might be in like a weird region where the Hessian's indefinite and stuff. Remember that the necessary and sufficient conditions for a minimum were gradient 0 and Hessian positive definite, right? So if you're at a minimum, then you should be taking full steps. So like basically at the very end of this, you're taking full steps and it's full Newton and it's like before and you get like the exact answer as long as the function's reasonably nice. Yeah, does that make sense? So these are basically, and in this, you can check, you should go look at this. This is only doing regularization and backtracking on the first step. After the first step, you're close enough to the bottom that you don't need it and it just goes. So these things, they both drop out. If the Hessian's positive definite, you're checking it, right? So if it's already good, you don't do anything. Same with the line search, you check the full step first. And if it's good, you accept it and you don't do it, right? So these things are basically like sort of fail safes that kick in only when necessary. Yeah, make sense? Cool. Yeah. Did you have a question too? Yeah. Oh, cool, cool, cool. All right. Everybody good? Yeah. Yeah, yeah. You can. Yeah, yeah. So I mentioned that before, right? So if you so the next fancier version of this line search thing is called the Wolf conditions. These are called the Armijo. It's called the Armijo rule or the Armijo condition. Wolf, WOLFE, is the second order version that uses the Hessian as well. Yeah, yeah, yeah. So they're more expensive, but like they're often worth it. There's way fancier line searches. There's the Wolf stuff. There's a very common strategy is to use a cubic approximation when doing these things. So there's all kinds of fancy things that you can do. There's actually like still research on line search methods. Um, yeah, cool. Yep, you bet. All right, everyone cool? All right, keep trucking then. Okay, so that's the line search thing. And basically we're good here. Yeah. So kind of the overall takeaway message from this whole thing is that Newton's method with kind of simple, what we call, again, globalization strategies with sort of simple and cheap modifications. And kind of the full story there is that we talked about this quadratic convergence rate, right? That it converges super, super fast. That's only true when you're in the basin, like close to the answer, right? When you're far away, it can be bad. And these hacks are basically to try to, they're sort of to try to get you to limp far enough along until you're in that basin of attraction where you get the second order convergence. So, but yeah, basically with these tricks, like this is Newton's super effective. And remember, this is only finding us a local optimum based on where we start, right? So we give it a guess, and essentially we're going to just end up in the relatively, like more or less the closest minimum, closest local minimum to where we started. So that's all we can ever hope for, local minimum. But this works great once you do these tricks, right? We fixed the problems. It works. I promise. Okay, cool. So that's that story. Everyone good? Yeah. Yeah. So if you were, sadistic and started it right on that maximum where the gradient is zero, it would say, it wouldn't do anything, right? Because it's ultimately it's like a scaled version of the gradient that you're computing here. But the odds of that happening are like essentially zero. Like you would have to do that on purpose. In fancy math terms, it's a set of measures zero, at least here, right? Like you would have to try. And if you're epsilon off of it, then you would sort of fall into one of the other things. There are nasty functions where there's like, say, big flat spots, right? Where you could get stuck. Um, but, you know, in most cases, yeah. So you can make up nasty functions where you have problems, and you can start in really, really terrible places but you kind of have to try for that second one. Yeah. Oh, it always is. Yeah, yeah. So the function has to be like C2 smooth. There's technical conditions on the function that yeah. So it obviously has to have two derivatives for us to do this, right? It turns out Newton's methods still work on functions that are less smooth. You can still do this on like C1, even C0 functions. Um, it still works, but you lose the convergence rate. So if I were to do this on like some weird function with kinks in it, like C1, it'll still work. There's some details on how exactly what matrix you're using in there instead of in those situations, but it still works. But you lose the fast convergence. Fun fact. There's all kinds of papers on like semi-smooth Newton methods for this kind of stuff, if you're interested. Okay, I think we're good. So yeah, we're gonna kind of change gears now and go in a slightly different direction. So that's like your last chance on this Newton stuff for a bit. Okay, cool. So everyone's happy. Now we're gonna talk about equality constraints. Who's done this before? Constraint optimization. Yeah, like one person, two people, very few. Cool. So I will, that's for calibration. All right. So just to tell you what we're doing. So we did this already, right? We have like our min f of x. And now the new wrinkle is we're going to say, do that subject to some constraint function, c of x equals 0. So I want to minimize f of x subject to having this other function c of x equals 0. And so just to kind of like be super clear, right? This is our cost thing that we were doing before, and it's a function that eats a vector, spits out a scalar, and the scalar is the thing we're minimizing, right? Got to spit a scalar out, and then this function, this can be vector valued, and so it's eating that same x vector in Rn, but it can spit out another vector of in Rm. The way to think about that is if you have multiple constraints, you can just stack them up into one big vector function and have a whole bunch of these. Yeah. You cannot have more constraints than decision variables. So generally, m here would be smaller than a. Yeah, I know. Otherwise, it's like over. It'd be like if m was bigger than n, you'd probably have an infeasible problem that doesn't have a real solution, right? Okay, cool. So that's what we're doing. So let's draw some pictures here and like talk about what we're trying to do. So, so what we're going to talk about now are what are called first order necessary conditions. So this is like slightly generalized version of the gradient equals 0, right? So for an unconstrained problem, the first order necessary condition is just gradient equals 0. We need a flat spot. In the constrained case, it's a little more complicated, but it has a very, very obvious, like in words, I can say it and it's clear and obvious. When I write it in math, it gets a little weirder. It's like there's a couple of logical leaps you have to make. So first order necessary conditions. So the first one is we need, and this is how you generalize that gradient equals 0 thing. So we need the gradient of f to be 0, but now only in the free directions. So we want the gradient to be 0, but we can't do anything about it in the constrained directions. I can't move in those constrained directions. So I'm only going to require the gradient to be 0 in the directions I can actually move in. So in general, grad f will be non-zero, right? But it's only allowed to be non-zero in the directions I can't move because of the constraint. Make sense? So that's the first one. And then 2 is we need to satisfy the constraint. So it's those two things. The second one's obvious, right? The first one, like when I say it in words, it's obvious. I need to zero out the gradient in the directions I'm allowed to move in, but not in the directions I can't move because I can't do anything about it. So now what we're going to do is try to translate that first statement into like a mathematical, statement. And I'm going to draw a picture to help us do this. I'm not the best at drawing pictures, so bear with me. So I'm going to draw like a top-down view of a bowl. So think, here's our quadratic bowl. I'm going to draw the level curves, right? So imagine you're just looking down at the bowl, and this is like, the level curves of. So we got a bunch of circles. And so the minimums at the origin say, right, and I'm looking top down, and these circles represent, sort of sections out of the bowl. Everyone cool with that? And let's draw a constraint in here as well, or add it. So let's say the constraint is going to be like this line here. So this line is the line c of x equals 0. And what this means is, I have to be on that line, right? So I'm trying to minimize that bowl subject to I'm only allowed to move on that line. So these guys are level curves of f, and then that line's my okay. So and then I've got f is in this case R2 to R. We're in the plane, and then C in this case is also R2 to R because I can only have one constraint, and otherwise I've got nowhere left to go. If I had two constraints here, I'd be stuck. I've only got 2 degrees of freedom to begin. Okay, so here's the leap. So we've got these level curves. On one of these level curves, the gradient is orthogonal to the level curve, right? The level curve is sort of where the f is a constant value, right? And so if I imagine my bowl, if I'm going uphill, it's got to be perpendicular to that level curve, pointing up, right? So pointing outward in this case, right? So let's draw some of those gradients. These are going to look like this, right? So that's like a grad f there. You know, this is a grad f here. Is that cool with everybody? Like down here, we'd have a grad f this way, right? Okay, and then similarly, our C up there, we're going to have like grad C perpendicular to the line. So this is grad C. That makes sense to everybody? Cool. Okay. So same deal, right? The line C of x equals 0 is a level curve of the function C of x, right? So it's decreasing in some direction, and that's got to be perpendicular, right? Okay, so that's cool. Okay, so we're going to take that statement that grad f has to be 0 in the free directions and like turn it into almost like the opposite statement with this picture. So if we think about what that says, grad f has to be 0 in the free directions. It means that grad f can only be non-zero in the constrained directions, right? So those are just like, opposite statements of the same thing. And so I'm going to write that down. And that's kind of the version that we actually write in math. So it's saying any non-zero of grad f must be normal to the constraint surface or manifold or whatever you call it. So if I look at my picture up there, what that's saying is that grad f has to be parallel to grad c, right? Grad c is normal to the constraint. And so if I say any non-zero component of grad f must be normal to the constraint, that's saying any non-zero component of grad f has to be parallel to grad c. Parallel, but not the same, right? So I can scale it. Everyone cool with that? So that's what we're going to write down now. So this statement is in math is grad f plus some scalar times grad c. And the scalar is, we're going to call lambda, has to equal 0. So this is saying, I can have grad f not be 0, but whatever's not 0 there has to be parallel to grad c. Equivalently, I have to be able to find some scalar that I multiply grad c by so I can adjust the length of it so that they match up. So I have to be able to like choose a lambda such that those cancel each other out, and then this is 0. And in this case, right, lambda can be positive or negative, whatever. That's the parallel thing. Does that make sense to everybody? So if I go back to my picture, that happens right over here. Negative something, I would be able to scale those so they lined up and canceled each other out, right? All right. Hopefully that made sense. Any questions about that idea? It's like a bunch of verbal like gymnastics, but it's like literally that's all it's saying. Okay, cool. And then we call this lambda thing a Lagrange multiplier, or often in optimization speak, a dual variable. Okay, who's done Lagrange multipliers somewhere before? Like most people probably, yeah. Did you have it explained any way like this before? No. Curious how. We can talk about this later. If anyone's got other. Cool. So that's the picture. Okay, so that's the scalar version. So we did this in the plane, and lambda is a scalar. And then if I have, higher dimensions and I have more constraints or whatever, no big deal. These things just turn into vectors. And we get the following. We would get partial f partial x plus lambda transpose partial c partial x equals 0. And then lambda is a vector in Rn. So it's the dimension of the constraint, right? The output of C. Okay, so that's the general version. And based on this expression that we just wrote down, we're going to define this function called the Lagrangian. So this is L, Lagrangian L of x and lambda, and it's equal to just our original function f plus lambda times the constraint. Why did we define this function? Because it lets us like very nicely, compactly write down all of this as just the gradient of the Lagrangian equals 0. So it's almost back to what we had before, where it was just like grad f equals 0. Now we just take grad L with respect to both x and lambda and set that equal to 0. We get the same sort of just gradient equals 0 condition. So this thing is called the Lagrangian. And now in terms of this guy, we have sort of the obvious thing we can write. I'll write it like this, grad x of L. So this gives us what we had before. So I'll write it, the transposed way to give you both versions. We get this guy. That's what we just derived with our picture. And then if I take grad with respect to lambda of this guy, that just gives me back the constraint, which has to equal 0. So those are our condition 1 and condition 2. So now you can write the entire thing as just grad L with respect to everything equals 0. It's kind of slick. Cool. Everyone cool with that? Probably some of you have seen this stuff before. Yeah. Lambda. Yeah. So the gradient of that thing with respect to lambda just gives you back the constraint, right? Because it's the Lagrange is lambda times the constraint. We take the gradient with respect to lambda, just get the constraint back, which is our second condition. So it's just like a pretty compact way of like writing all of that, like summarizing it all into like one thing. Okay, so that's the first order necessary conditions. We make up this thing called the Lagrangian that like sticks the function that we're trying to minimize and the constraints together with that Lagrange multiplier thing function. And now we're back to just like set the gradient equal to 0. And so how are we going to solve this thing? Who has some ideas? So I just got us back to a thing that says gradient of L equals 0. Now we got a fixed point problem again. We're going to just throw Newton at the entire thing. So we're going to throw Newton at setting grad L to 0 with respect to both x and lambda at the same time. We're going to just do fixed point on both x and lambda, solve the whole thing. Let's write that down. So I've got the first one that we're trying to do, grad with respect to x. And what I'm going to do is like write it down, with some delta x's and delta lambdas and do our Taylor expansion trick like before. So we got x plus delta x, lambda plus delta lambda. I'm going to write this whole thing down. So you've got the first term where we are right now. Then we've got partial of this with respect to x times delta x, which is going to be d squared L dx squared times delta x. Then we've got d squared L dx d lambda times delta lambda equals 0. Everyone see how I did that? Just, yeah, put the next derivative with respect to x of that whole thing from up here, right? So ddx of grad f is, the Hessian, blah, blah, blah. And that second term, that d squared L dx d lambda, that like mixed partial term, that's just the Jacobian of the constraint. This is partial c, partial x. If I look up here, right, if I look at the original Lagrangian, if I take partial respect to lambda, I get back c, and then if I take partial respect to that, I get dc dx. So that's where that Jacobian thing comes from. So if you're like half following this, I highly recommend just going back and like doing this yourself to like sanity check the algebra. Okay, cool. So we got that, and then the other one we've got to do is we've got the second set of things here. We do the same Taylor expansion thing down here. We get c of x plus partial c partial x times delta x equals 0. Like doing out the algebra and doing the Taylor expansion thing. Okay, so what I'm going to do now is take those two sets of equations where I just did the first order Taylor expansion with respect to like delta x, delta lambda. I'm going to package all of that up into one like matrix equation, which is the thing we're going to solve in our Newton solver, right? If I go and do that, I just stack everything up. It's going to look like this. So I've got d squared L dx squared. So this is the first line, right? So I got d squared L dx squared times delta x. And then that like mixed partial term, d squared L dx d lambda, which we just saw is actually just partial c partial x transpose. So I'll just plug that in. I got partial c partial x transpose. And then downstairs, I'm going to get partial c partial x from the second line. And that's all there is. And I'm going to get a 0 block over here because that doesn't have another derivative with respect to lambda. There's no lambda in it after I take one derivative. So this times delta x, delta lambda equals minus grad x of this guy, and then constraint violation. So this guy comes from like up here, this whole thing. If I rewrite this, it gives me the usual, it's just the Newton step on the constraint. That's how I got that second line down there. Okay, so this is just me rewriting that Taylor expansion thing and solving for delta x lambda, which is what we do in Newton, right? So that's the Newton step. And this thing shows up so much in optimization that it has a name. This exact like matrix equation that we just wrote down, this is called a KKT system. And this is like bread and butter of like numerical optimization. This shows up so often. There are like specific like linear system solvers for this. There's all kinds of stuff. It's a huge deal. The reason it's called KKT is because these optimality conditions we just wrote down are called the KKT conditions, which is Karush, Kuhn, Tucker, where three guys that like independently derived these things in like the 20s, 30s. One of them, I think, Karush was like it was in his master's thesis or something. It was like maybe even an undergrad thesis. He was like an undergrad when he like derived this stuff in his like, it was in the 20s. So I guess the bar was lower back then. But so they're named after those guys. Actually, the KKT condition, strictly speaking, refers to the inequality necessary conditions we're going to get to. But this is still like called, you'll often hear people just say KKT conditions for everything. So this, even the unconstrained grad equals 0, you'll people call that KKT conditions. So KKT conditions, when we write down like the Newton step on the KKT conditions, and we get this specific matrix equation. So if we take a look at that, can you tell anything about that matrix? Like the obvious thing is it's symmetric, right? So we get like that Hessian thing in the top left has to be symmetric because it's a Hessian. And then the lower left and top right block are transposes of each other. And then you've got a 0 block. So that matrix is symmetric, which is useful. Okay, Okay, so I don't know, that's a thing. We should know about that. We'll use it. There's one other thing I want to tell you about this before we move on. So there turns out there's sort of a slightly nasty term in this that's expensive, that is annoying to compute. So people often leave it out. And when you leave that extra term out, it's called the Gauss-Newton method. We'll do that real quick. Has anyone heard of Gauss-Newton before? Yeah, where? In controls class. That's surprising. So it's very, very common in statistics. It's like the standard method for nonlinear least squares. Fun fact. But yeah, I mean, it is common in numerical optimal control also. So I'm slightly, which controls class was that in? Oh, okay, cool. So here's where that shows up. So if I look at that Hessian, that d squared L dx squared term, it's equal to the Hessian of f plus this extra like second derivative term of the constraints that looks like this, partial respect to x of like dc dx transpose lambda. So I actually like, the reason I wrote it like this is if I go and like actually sort of product rule that derivative in there, I get like d squared c dx squared. So like the Hessian of the constraints, or it's called the constraint curvature term. And if I think about that, so if c's a vector function, each a vector spits out a vector, its first derivative is a Jacobian matrix. What's its second derivative? I mean, shape-wise, dimension-wise. The first derivative is already a matrix. If I take another derivative, I'm taking a derivative of a matrix with respect to a vector. I get a third rank tensor. Anyone know what those are? This is like, basically the way I think about it is like a 3D matrix. So it's got three dimensions, right? So matrix, right, I've got rows and columns. A tensor, I've got the rows and columns, and then I have another index that goes this way. That's super annoying and super nasty. And for large problems, that's gigantic, right? So if we're talking about like a big problem where we're already dealing with like a million dimensional problem or whatever, the Hessian's already like million by million, say. This tensor thing's now a million by million by a million, which is like super terrible. We don't want to do that, right? So if it's a small problem, it's all good. Like, you know, fine, you can do it. But often this term is very annoying to compute. So we just drop it. Um, so when you do that, so we'll call this the constraint curvature, right? Because remember, second derivatives are curvature. We measure curvature. So this is like the constraint curvature. In the picture I drew, what's that term? Someone said it. Be louder. It's zero, right? Because it's a straight line. There's no curvature. That's a linear constraint. Right? A constraint curvature is a straight line that has zero curvature. So there's no second derivative, right? So in this case, it's zero. But in general, you know, nonlinear constraint. Um, so when we leave that out, it's called Gauss-Newton instead of Newton. And this is really common. It's again, it's the standard thing to do in nonlinear least squares. So in a lot of statistics things, you'll do this. And it's pretty standard to do it in control as well, like trajectory optimization methods that we're going to talk about. It's kind of the standard move. What happens when you do this is you get slightly slower convergence. Per iteration. So it might take you a few more iterations of the solver to converge. But the iterations are cheaper, right? Often a lot cheaper. So it obviously depends on the problem, but in a lot of cases for like larger problems, Gauss-Newton often wins in terms of wall clock time. So that's kind of why people do it. Okay. Any questions about any of that stuff? Okay, so let's do it. So some equality constraint stuff. Clear these out. Like tease the good stuff. All right, so here's what we got here. So I'm going to make up like a cost function, a quadratic cost function. So I'm basically going to draw roughly the picture I just drew by hand, though with a slightly nonlinear, weirder constraint function. So I got a nice quadratic bowl. This is my cost function, right? Just like x transpose qx kind of thing. There's q. And then here's my constraint function. So it's nonlinear. I'm just making up like some quadratic constraint. Cool. And so same setup we just did. So I'm going to plot this top-down landscape view like we just drew. So these rings are my level sets of my cost, right? So it's got a minimum in here, right, in the middle of that inner circle. And it's doing this away from there. And then here's my C of x. So here the deal is I'm only allowed to move along the yellow curve. C of x has to equal 0. So the minimum in this case, right, it's going to be like as close as I can get while being on the yellow line, right? So it's probably somewhere intuitively, the minimum's right about there somewhere, right? Cool. Okay, so that's it. So now I'm going to write down my Newton step. So first is the Hessian. So I'm in this case just going to like use for diff, right? So I hand wrote the Hessian of f because that was easy. And then I'm going to use for diff to get that second curvature term because I want to write down. So this is exactly what I just wrote. It's like ddx of, partial c partial x times lambda, right? And then let's see, here's the constraint Jacobian, dc dx. We'll call that big C. Here's my KKT system. So it's H C transpose C 0, like that same matrix I just wrote down. And then this is the Newton step, right? Backslash on that guy. And the right-hand side vector is grad F, which is that guy, right? So it's grad F and then the constraint Jacobian multiply term. And then the bottom is minus the constraint violation. All good? And so I compute the step, do my thing, compute the deltas, make my step. Like that's the whole thing. So in this, I have not yet implemented the tricks we talked about, right? The globalization strategy, straight up Newton step. Cool. So now let's do it. Let's try something a little easier first. Let's try like starting, so let's start down here. So this is on the constraint. And we said the minimum somewhere over here, probably, right? So let's see what happens. So we'll take a Newton step. That shot way over here. So it basically shot in the direction of the minimum, which is good, but it shot way off the constraint. So one thing, right, to keep in mind is, so if we think about what happened, this thing's linearizing the constraint and then taking a Newton step along the linearization of the constraint. If I linearize the constraint right here, I get this like tangent line. And so what this is exactly what you would expect if you understand that, right? So it's minimizing a quadratic approximation of f on the linear approximation of the constraint. So, okay, cool. I'm going to move in the direction of the minimum along that tangent line. Exactly what you'd expect. But if I were thinking about this in terms of like overshoot kind of ideas, like we just talked about, that's probably not awesome. I might want to think about, some kind of backtracking strategy to keep me closer to the constraint manifold. So one thing to keep in mind, right? Even if I start this with a feasible point that's on the constraint manifold, the Newton algorithm can step off the constraint, which is maybe annoying and actually causes problems in general. And there's all kinds of things to talk about there. But let's see what happens. I'll take another couple steps. So yeah, so now, I went over here. Then what's going on here is I'm going to linearize the constraint here, which is like this tangent line. And I'm going to try to step back onto that tangent line. So that looks about right. And then as I kind of take another couple steps, that's 3 steps, 4 steps on there now. So it's similar convergence. I took like 4 steps and I basically got the exact answer. If I take another one, right, I'm not going to. And it's exactly kind of where we thought, right? It's right about like the closest point on this curve to that minimum. Cool with everybody? Yeah. Does anyone have questions? I'm gonna try stuff. Yeah. Yeah, we're gonna do that in a sec. So yeah. Yeah. I mean, this is just smushing those both together. So the second line of that is literally the root finding on C of X, right? So the second line is root find on C of X is literally the Newton step on that root finding problem. And then the top line has the Newton step on the objective. So you're literally just smushing those together into one problem. Yeah. So in general, with this, what I just wrote down, I don't have any regularization line search stuff on here. So in general, no. If we need to go back and do the regularization line search stuff. And there's slight tweaks you have to make in this setting. So we're going to talk about that in a little bit. I did want to point out so let's try one other starting point here. The one I had in here before, actually. So these are good questions. We're going to do all that stuff. The line search regularization story is a little more complicated in this setting. So we're going to have to do a little doggle into that. So let's start in a more annoying point. Oh, yeah, up a little bit. That's what I want. Okay, so let's start up here and see what happens. This is kind of fun and gets at this whole thing again. So I'm going to take a step. All right, here we go. Oh, that's right. I need to go down. Okay. Okay, step. That makes sense, right? I'm stepping along that tangent line to the constraint towards the optimum. Cool. Take another step. That sort of makes sense. Cool. Making progress, getting close to the constraint, right? But going towards the minimum. Take another step. That sort of makes sense too, right? Tangent line towards the optimum. What happened there? It went backwards, kind of in the wrong direction. Well, there's infinite places where C of X is 0. This whole yellow line is all places where C of X is 0. What I'm trying to do is find the closest point on this curve to this minimum over here. So what I should do is kind of keep moving around here to up here, which I was doing. That kind of all made sense. But now I just took a backward step in the wrong direction. Now I'm up here. You'll see actually what's going to happen in a second is I'm going to converge to some random point up here. What the hell? You don't have any thoughts on what's going on there? Yeah. It got stuck in some kind of local optimum, but this is like a pretty weird place to get stuck, where it's not satisfying the constraints or the any of those necessary conditions. It's a very weird situation. Anyone have any guesses of what's going on based on our previous, weird Newton things? Where did we see Newton go the wrong direction before? And the Hessian's indefinite, right? Then it can go uphill instead of downhill. So this is a good guess. Let's check the Hessian, and then it's already there. Okay, so what I'm doing here is checking the Hessian of the Lagrangian, not just the Hessian of F. So in this case, F is quadratic. So the Hessian is just the Q matrix in the middle, and I made that up to be convex and nice. So that was positive definite. But remember, the Hessian that's in my problem here has that plus that constraint curvature term. And it turns out that constraint curvature term can do anything. And what we just found here is that is most definitely not positive definite. So that's messing us up. And it made us go in the wrong direction, just like before. So this is so first of all, you have to regularize like before, even if your objective is convex here, because the constraint curvature term can mess you up. That's what's happening here. So our Hessian of F there, del squared F is nice, but the second term is what's screwing it up. The other thing though is if I do Gauss-Newton here, I just get rid of this guy. So that's yet another pro for Gauss-Newton is it gets rid of that term entirely, so you don't have this problem. So those are two things. So let's go try that. So here's the Gauss-Newton version, which we said we were going to do. So I'm doing the exact same thing, except now my H is just the Hessian of the objective, and I threw out that constraint curvature term. So let's see what that does in the same scenario. I'm going to start at the same spot up here. And remember what happened last time. Let's take a look. So makes sense, right? Same thing as last time, more or less. But now I keep going. I'm doing kind of what I would expect. I'm stepping around, and then sure enough, I end up at the right spot. So it very much was that constraint curvature term in the Hessian that was messing us up and giving us indefinite Hessian. So so this is more motivation for doing the Gauss-Newton thing rather than the full Newton thing. And then just kind of buyer beware kind of thing. even in these situations where F might be nice, C might be nasty, and you're going to still have to do some regularization stuff. It's not, we're going to have to talk a little bit more to like sort of give you a little bit more to show you how to regularize in this scenario. It's a little different. So that's coming, but that's just kind of the story. Okay, any other questions about this stuff? Okay, cool. So we did this example. And if you go run the code yourself, which you did, like the 2 points we did were like the first one was like -1, -1. And the second one was -3, 2 was the weird one. In that case, right, full Newton gets stuck in a weird spot, and Gauss Newton actually does fine. Okay, so takeaway here is you may still need to regularize that top left block, that squared L EX squared thing, even if the Hessian of F is nice. And then Gauss Newton here, you don't necessarily have that problem because you just throw that term out. And that is another sort of pro for this guy. And a reason why it's popular. Okay, any questions about this stuff? We got Lagrangian, Lagrange multiplier, KKT conditions, KKT system, Newton's method, all that good stuff. A lot of stuff. There's usually some like that leap from, to get those KKT conditions is a little gnarly. So everyone cool with this stuff? Any other? Yeah. So you still converge to the exact answer the same way. You still get like super linear convergence. You still get good convergence. It's slightly worse convergence than the full Newton thing. But you still get this like good tail convergence stuff where you get the answer. Like roughly speaking, like if full Newton's like 3 or 4 iterations, this might be 5 or 6 or something like that. Yeah. Sorry, if that's just a 2. It's d squared L dx squared. Someday I will LaTeX all of this, and you will not be so frustrated by my terrible handwriting. But please do ask. There is confusion. Okay, cool. Everybody happy with this? All right. So now that clock is all messed up, huh? What we're going to do now then is talk about inequality constraints. And we're probably going to have to keep doing this into next time. But we'll get started and at least give you the intro. So what we're going to talk about now is same deal, minimize F. But now instead of C of X equals 0, we're going to talk about C of X less than equal or equal to 0. And in this case, we're just going to talk about the inequalities for now, because it's like kind of a modular thing. Like we're going to talk about inequalities to do both together. You just take the stuff we just did and smush it together with this, and you're good. You have the whole thing. Okay, so just inequalities. It looks like that. And then once we're done with all of this, you just put it all together. Okay, so the first order necessary condition story in words is identical. And that's really the story, right? That's the intuition. That's the picture. And by the way, these are the actual KKT conditions in this situation. Okay, so we have, again, grad f equals 0 in the free directions. So in any direction I'm allowed to move, I need to zero out the gradient. I need to be at a local flat spot. But obviously I can't do that in the constrained direction. And then the second one is just satisfy the constraint. So it's the same story as before, but the free directions story gets a little more gnarly now. Gnarly enough that I will make a new page to write them down. Okay, so I'm going to write these down and then we'll like talk through it and interpret it a little bit and draw the picture. I'll write it down before I draw the picture. Okay, so it's similar to before, but has some extra bits. So we're going to have this similar gradient condition with this Lagrange multiplier thing. So this guy has to equal 0. This is exactly the same as before, and it's getting at this parallel sort of, situation where if grad f is non-zero, it's only allowed to be non-zero in directions that are perpendicular to the constraint manifold. So that's what that says, right? Same as before. But now we've got some extra stuff. So we have this, we have the constraint satisfaction thing. So that's the same as before, basically. But now we have some extra stuff. So the first off is before, remember, lambda could be anything. It could be positive or negative and kind of point in that direction, or whatever you needed to make that first equation hold. But now, essentially what we've got now is a one-sided version of what we have, right? So instead of being on the line, that line is now, anything on one side of that line is legal. So what that means now is I have to worry about the sign of lambda. It can only point in one way, but not the other. And so we're going to write lambda has to be positive. And then the last one is lambda times c has to equal 0. And we're going to write this, I'm going to write this two ways that are equivalent. In the scalar case, these are all, whatever. It's lambda times c equals 0. And that weird circle dot thing, that's just an element-wise product of two vectors. It's called a Hadamard product. It literally just means take every element and multiply them together and get a new vector, right? I think that's dot times in that. Okay, cool. So there's names for all these things. So this is called, this whole setup here, these are called the KKT conditions. So you can see like some master student in 1930 or whatever coming up with this pretty good, I guess. This first one, the gradient equals 0 thing, is called stationarity. These all have names. Stationarity. This is called, so we said that the lambdas are called dual variables, right? The x's are called primal variables. So primal dual, I don't know, that's the name. So this one's called primal feasibility. Feasibility just means it satisfies the constraints, right? So primal feasibility means x satisfies its constraint. So there you go. And then as you might expect, the lambda greater than or equals 0 is called dual feasibility. So the dual variable, i.e. the Lagrange multiplier lambda, also has to satisfy its constraints. It has constraints. In the equality case, there are no dual feasibility, whatever, because it can be anything. And then this last one that says lambda times c has to equal 0 is called complementarity. Okay, so let me talk through these and like what's going on. Sort of where that complementarity thing is coming from. So let's say, let's think about, okay, so like now, I've got this constraint. I'm like, gonna go hit it or whatever. So let's say I'm up against the constraint. We call that active. Say the constraint is active in that case. And then basically what we're doing is like turning on the constraint. So let's think about that case. So if the constraint's active, that means that c of x equals 0, right? So that primal feasibility thing holds with equality. So if C equals 0, I go check my complementarity. So it says C times lambda has to equal 0. That means one or the other has to be 0. So what's that saying? That if C is 0, then lambda is allowed to be non-zero. And in that case, I'm exactly in the equality constrained case. So lambda's full, C 0, and we're back to the equal. It's exactly the same as the equality case, right? So let's write that down. So we're on the constraint. Then we've got C of x equals 0. Then I can have lambda be non-zero. And we're in the exact same situation as equality constrained. And that complementarity is basically encoding on-off switching of the multipliers of the constraints, right? So this is same as the equality case. And then if I have if the constraints are inactive, meaning I'm not on the boundary, I'm somewhere in the interior, that means C of x is strictly less than 0. Then if I go look at my complementarity, if C is non-zero, then lambda has to be 0. Condition. So it basically means I'm turning off the Lagrange multiplier. So if I'm on the boundary, then I like that complementarity basically turns on the Lagrange multiplier. If I'm off the boundary, somewhere in the feasible region, the complementarity constraint, like that complementarity condition, basically turns off the Lagrange multiplier. And then it just removes that whole term from the problem, right? Everyone see that? So the way to think about that complementarity thing is it's on-off switching of the Lagrange multiplier term and all this stuff. When it's switched on, I'm on the boundary, then it's just an equality constraint. When I'm off, it switches the whole thing off and all the constraint stuff drops out. Everyone see that? Cool with that? Cool. So then to equal 0, and this is the same as the unconstrained case. Okay, and yeah, the like kind of key idea there is complementarity, like basically encodes like on-off switching of like all the constraint terms. Okay, any questions about that? Yeah. Has to be strictly positive. This needs a picture, which we'll do. We are kind of, 4 minutes left, so I don't want to, I'll do it next time. But if we go back here and look at this, I'm going to draw this. I'll draw it next time because we were like kind of out of time for this. But what's going on there? Let's say, okay, so this curve down to be parallel, but I'm only allowed to have it. I need the gradients to be sort of, let's see what's the right way to say this. I basically only want the constraint to push and not pull. That makes sense? Yeah. That's maybe the most good. So basically that grad C term, that's the like direction of the constraint force. Make sense? So like if I'm trying to go here, so I'm trying to minimize, say this is the and what that's going to do is like slam me up here. I want to push off the constraint in this direction. I don't want to pull the solution that way. So that's what it's doing. The sign condition makes it so that you can only push away from the constraint and pull, not pull towards the constraint and pull. In the equality case, I could do both. Right? I need to keep it on the line. So if it's over here, I need to push more pull, depending on which side I'm on. Here, one-sided, I only want to push away into the feasible. I don't want to pull. Go the wrong way. Does that make sense? Yeah, so that's where the sign condition comes from. And there's the really, really good intuitive way to think about this stuff is always, for me at least, is mechanics problems. And this is on your first homework. It turns out like the like super intuitive way to get at this equality stuff is to think about a falling brick, like a falling particle. So you think about like I throw the brick and I have like the ground or like ice. I throw it on like a sheet of ice. Then it's the equality constraint is the brick's not allowed to go through the ice. That's, C is greater than or equal to 0. The Lagrange multiplier is the contact force. So the ice can only push up on the brick. It's not allowed to pull it down. It's in the air. There's no force. The complementarity is 0. So like basically with that there, it's the height times the contact force has to equal 0, the normal force. Then when your constraint goes to, your height goes to 0, then you get a normal force. And the lambda is exactly the normal force. And it's just saying that the floor can only push up on the brick. It can't pull down. So you get this very, very nice intuitive picture. So that intuitive picture is on your homework. So you should check that out. And that's for me, that's like the right mental picture. It's like, okay, you're thinking about contact force and gravity and, F equals ma, and it's like super clear then in your head and gives you a really good intuition for this stuff. And complementarity in that context is literally that you can't have force at a distance, right? You can only have force when the things are touching each other. Yeah. That's right. So this is a subtle point that's good. We're going to do this next time because we're out of time. But it turns out you can define these conditions. Oh yeah, this is off now. So this whole mess here, turns out like there's multiple equivalent definitions here, and there's the sign choices matter. So the idea is that that Lagrange multiplier term, stationarity line, is a penalty for constraint violation. That's the way to think about it. And you need to set up the signs so that it's penalizing. So if lambda's positive and I violate, so if lambda's positive, I'm violating this positive. Should cost higher. If I make the constraint positive, then positive is good. If I lambda positive, C positive, then to be a penalty, I need to penalize when C is negative by theta minus. It's actually like up to, it's like a, sort of choose your own adventure. And there's like multiple sign conventions you could go with. You could make this. Right. Because otherwise, if you don't get that right, you're encouraging it to violate the constraints. Right. So that's not what you want. That makes sense? Okay, so we'll talk about that next time. I'll draw the picture next time. We're out of time for that. I think that's where